first thing I would deny is that it was a title of my choosing. When you're asked by Steve, would you like to come to the meeting, and by the way, would you give a talk on Gelfand duality, constructive Gelfand duality, then you accept.
I did give you the option.
Well, you did give me the option, yes. Anyway, it was, in a certain sense, a very foolish thing to do, because this was, when it first appeared as a preprint, it was an extremely long preprint, so long that it never got published, as I shall say later on, and it didn't get any shorter. Just while we have this screen on, just to say that all the papers that are referred to in it can be found at my website at Sussex. Due to a little tussle involving the fight to save the LMS joining with the IMA, someone very kindly hacked into my desktop computer at home, sent a very rude message to the Vice-Chancellor, as a result of which the Vice-Chancellor, or the Registrar, stopped my access to my mail account at Sussex. So the Sussex mail address for me doesn't work. So thank you very, very much, Cambridge alumni, for giving me that address, which I can continue using. The next thing is somewhat sad for me. I hope I don't break up in the middle of it, but to give a slight dedication for this talk. Those of you who may, for some obscure reason, have watched Channel 4 television at 9 o'clock for the Tuesday, Wednesday, Thursday after the August bank holiday, will have found yourselves watching a series of very incisive documentaries into the police operation that ran a few years ago, called, I think, Sentinel-2, looking at sex trafficking in the UK. If you survived till the third programme, since really the programmes were pretty tough going, you may, just as you went out to get a coffee at the end of it, have seen a brief dedication to the person who commissioned those programs, which is Jean and my daughter Sarah. Sarah, unfortunately, this was her last series of documentaries that she commissioned for Channel 4. She died at the end of January last year in what has turned very tragic circumstances. So I would like to just say that before the meeting. So this is the first meeting since that happened I've been to. So I want to tell you something about Gelfand duality, seen from constructive eyes. And it goes back a long way as far as I was concerned, and we'll see it goes back a bit further than that in its origins. So going back to 30 years ago, when it began to be realized that a technique existed for constructing locales by using geometric theories, propositional geometric theories, that describe what classically were the points of the locale, even though, as Marty was explaining, the points need be existing in constructive concepts. And so this opened up the possibility of making various proofs constructive that, in their classical form, had either been equivalent to or virtually equivalent to forms of the axiom of choice. In a certain sense, for me, the beginning of all of this lay before I was really in contact with it all, almost exactly 10 years earlier, so in 1970, when Bill Orvere gave a very impressive talk at the International Congress of Mathematicians in Nice on the work that had just been beginning to be done on topos theory in the sense that we now know it. And he wanted to emphasize in these the unity of the opposites of geometry and logic by indicating aspect of each to which the topos theory could be applied. And the first of these was to show that the unbelievably technically awful, in a sense, work that Monique Hakim had done on internalizing the construction of the spectrum of a commutative ring, which was something that Grothendieck wanted because he wanted to define things over things, and so he had to internalize all of these things. That this was one thing that it could be applied to, that the Newton's theory approach could be applied to. And the second was to the independence of the continuum hypothesis, that applied a Toepler's theoretic context to yield a categorical approach to the proof. Well, in the talk that Bill gave, the insights into these things were certainly present. The detail, should we say, was not entirely apparent, or in certain words one might say it was rather lacking. So let me start off with the spectrum of a commutative ring, because it gives a good example that we're going to be building on, and we're building on 10 years later. Bill's constructive insight was that actually when you're looking at prime ideals, the elements of the spectrum of a commutative ring classically, you shouldn't be. Because you don't want them constructively, because you don't do anything with them. What you do with an ideal is factor out by it and form a quotient ring. What you were actually wanting to do with the prime ideal was to look at its complement, the things that were not in it, and invert all of those to get a local ring. So instead of looking at prime ideals, which have one axiomatization, you actually are looking at what are called primes of the ring. Subsets that satisfy these conditions, and if you think of all the things that don't satisfy them classically, they give exactly the axioms for a prime ideal, but constructively this is what you want. The axiom that says that A plus B belongs to P implies A belongs to P or B belongs to P, the complements. I mean, think of that saying these things are invertible in a local ring, and you'll get the idea of what's going on. That is exactly the thing that gives you locality. I've written them down as entailments between propositions here about elements A. The P is purely symbolic, it's the prime we're going to construct. But if you have a model of this theory, classically an assignment of true or false to each of these propositions, then that satisfy all of these axioms, then what you will get is the complement of a prime ideal, or what you will get constructively when you internalize this in the topos is that you will get something you can localize with respect to. At the time, the statement that was made was, all you have to do is take these primes, form them up into a topological space, boom, you've got what Hakim was looking for. Unfortunately, that's not true. Joël and I, at the end of a seminar in Montreal in 1972, after an overall fact meeting in the summer, where this was exposed for the first time to the categorical audience, showed that, for example, the generic commutative ring, the classifying topos of the commutative ring, has absolutely no primes. Okay? But what we want is the locale of its primes. What Joël said at that point was something he had been pushing for quite a while, which was actually the way you should think of the spectrum is as a whole bunch of open sets on which a given element is non-trivial. He called this the universal support, and he had it as a distributive lattice. So he had a map that was universal into distributive lattices that took each element of the A of the ring to some element of that particular distributive lattice and satisfied what you may recognize the form of those things. It's exactly what we were seeing on the previous slide, written in a slightly different way. You might also notice that these are conditions classically satisfied by the Zariski opens of the spectrum. But we really just transcribed it when we look at Mulvey's axioms for a prime and put it in this entailment language, we're looking at exactly the same thing. Once locales became the flavour of the month, as they did round about then, not that they'd not been defined for some time before that, but this is really when they came to prominence. Really, Joël's thing would be rephrased as a universal support, taking values in a locale. So again, the same axioms, and then what one can show is that this internalizes into any topos. The locale that is universally constructed by means of these things plays the role of the spectrum. And in particular, if you go into sheaves of it, then you can generically invert over the support of each thing, each element, and that gives you a local ring, and that local ring over the spectrum is the, as it were, the scheme that has got out of that commutative ring in the original topos. So what we began to do at that time was to see, well, actually, since Mulvey said we shouldn't be taking the points to be the prime ideals, we should take them to be the prime, then actually look at the propositional geometric theory that puts for each element of the ring a proposition that gives you the sense to which you observe that that element of the ring is invertible. In other words, has support. And the conditions that you write down are exactly the conditions that classically give you the points you want, well, classically given that little constructive insight. So technically what we do is we form the Lindenbaum locale of that theory. It's exactly equivalent to the locale generated by the elements dA in the previous slide. So you can think of it as using algebraic properties of locales, or you can think of it in terms of the Lindenbaum algebra theory, which is the locale taken by the propositions generated by these primitive propositions, modulo provable equivalence within the theory. If you can prove that this proposition, not a primitive one, but something built out of it, is equivalent to this one. So, for example, we've got an axiom that says that AB belongs to P is equivalent to the proposition A belongs to P, conjunction B belongs to P. Then you squash those two things together, and then you order them, those provable equivalence classes, by provable entailment within the theory. So we then get a locale. That is the same thing as Joao was considering, but now we're getting it by writing down the theory of points, of what the points originally were. The only difference we've made is take into account we're working in a constructive context. Well, the second thing that Mulvey was talking about, I mentioned, was the continuum hypothesis. And where that met its downfall was when Tierney gave a talk at the same Oberwolfach meeting in 1972, wrote out his axioms for the reals, since everyone wanted to know what they were, and unfortunately they gave the wrong thing, as was rapidly pointed out. What you wanted was something that, interpreted in sheaves on a space, for instance, gave you the sheaf of continuous real functions on that space. The axioms he wrote down, I think I got it the right way around, gave the sheaf of upper semi-continuous real functions on the space. Very nice sheaf, but not what he was intending, not what the continuum hypothesis was wanting to be talking about. So in other words, all the rest of the machinery they had was fine, was extremely interesting, but the basic object they were talking about was not quite right. The constructive, there goes the lack of fonts on this poor machine, but you'll just have to fill in little bits. That if you want a real number, you have to take a pair of cuts, an open lower cut, an open upper cut, and together they satisfy various conditions, and I've written down what those conditions, how they would have been written at the time to describe a real number. And of course, if you do that, if you internalize that construction, then you do get the right thing, and from then on everything is okay. But once again, once one looked at locales, one saw that there was a very natural theory to write down that gave you the locale of real numbers, the points of which were the real numbers in the topos you were considering. The objective points of that would be the real numbers. And here is at least one theory that does the business. So just going through those, I'm looking at rational open intervals and picking up Martin's comment about observable propositions, observable properties. The property we're observing about this real number x, this is just a symbol, is whether, or the extent to which it lies in a particular rational open interval. We're allowing the possibility that R and S are not, as written here, such that we know that R is strictly less than S. In a topos it may be somewhere, it may be somewhere else that it isn't. So we put in axioms to start off with that says that our generic real number can't lie in it if the rational open interval in the lattice of rational open intervals is below the bottom, is the bottom. Equally well, it's certainly true that x lies in some rational open interval, and so on and so forth. The little symbol is rather below over on the right of the next line, meaning that this rational, we can write it down just algebraically, but this rational open interval has its closure contained inside the join of those two others. And in this case, we want the thing on the left to hold, and so on the whole way through. The last one, of course, is saying that every real number, if it lies in a given rational open interval, if and only if it lies in the join of the rational open intervals that are run below that. If propositionally it has that property. So then the locale of real numbers, that seems to be what it doesn't like. It's the minimum locale of this theory. And we can do the same thing for complexes. And the important thing is that you can actually work with these theories to prove properties of the relevant locales, local compactness, so on and so forth, the fact that they're regular, completely regular. All of these things work very, very nicely, actually working with the theory. So all we've done here is to change rational open interval to be a complex rational open interval. In other words, we are looking at a little thing here, and we're putting R, a complex rational, and S, a complex rational, at the corners. So this is the observable property that the complex number we're considering lies inside of that rational open square. Now does some very, very interesting things with its fonts. Complexes become S with a hat over them, so remember that. Every time you see it, you know what it means. So the complex numbers are the points of this locale, and so they are just the canonical models, the models in the topos you're taking it, of the theory that you're looking at. Well, Gelfand duality, of course, uses some of these things as ingredients. It's actually going to use both the primes in an appropriate enhanced form and the real and complex, or real and complex numbers. And this was put together. I had an idea of how one could go about proving it, what the steps would be. Bernhard Maraszewski and I were sitting in McMaster with 10 days to go towards the meeting on categorical topology that was held in Ottawa that summer. And I said, okay, Bernhard, 10 days we're going to prove Gelfand duality. And we did, although one should say very much that Joanne Pelletier and myself had been working through the summer on a constructive form of the Hahn-Banach theorem, and this really developed a lot of the techniques that we used. Over the next so many years, this got written up in detail and came to about 180 pages, which was deemed unpublishable. It was just too long. No one would want to do what was rather an obscure thing. So, of course, we did what always happens. We divided it up so that it became very much more than 180 pages and published it as 4 papers under the sort of unifying title of the spectrum theory of commutative C-star algebras. So the first talked about the notion of the spectrum of the C-star algebra. I'd actually talked about that at Oberwolfach in, I think, 1973 or 1974, and written down one version of the theory. But then we went on and proved the Gelfand theorem in constructive form, the Stone-Weierstrass theorem in constructive form, and finally there was a paper that appeared rather more prominently called a globalization of a Gelfand duality theorem that put all of this together. Now, my advice to anyone wanting to know more about this than I'm going to be able to say in the next how many minutes it is read the last paper and then dip back to the other ones if and when you need stuff. Each of them was written to be independent, so there's a lot of repetition that goes on, but it's the final one that brings things together in a readable form, and then if one ever wants to look at the details, you indeed can go back and do that. So the first of those papers found the proper definition of maximal spectrum. In fact, it found two proper definitions, the two that exist classically. One became the locale of multiplicative linear functionals, which, because we had previously called the locale of functionals of norm less than or equal to 1 fun A, we had to call this M fun A, and this was really then depended very, very heavily on work with Joanne Peltier. The second proved the constructive form of the Gelfand-Mazur theorem. I'll come to what it says classically in a moment. But this here was observing that there was a canonical map from multiplicative functionals to maximal ideals, if you want. We have to see what those are. That basically says take the kernel of a maximal ideal, of a multiplicative linear function, because it goes into the complexes. That would be a maximal ideal. Complexes being a field, this being surjective, and so this is an isomorphism of locales, and we're going to identify these two things. Sometimes we're going to use the multiplicative linear functional aspect, sometimes the maximal ideal aspect. Now you'll remember that S check means the complex numbers, so in Birmingham the third result showed that there was a Gelfand representation from A into S check max A, so that is from the original commutative C-star algebra into continuous complex functions on the spectrum, and that is an isomorphism of C-star algebras, and the final paper then tied all of these together to show you how an adjoint equivalence between that forms Gelfand duality. So what is that? Classically, it's the duality between the category of commutative C-star algebras and the category of compact Hausdorff topological spaces. So if you consider that and look at commutative C-star algebra, you form the space of maximal ideals in the Zariski topology. That gives you a compact Hausdorff space. And to come back the other way, take any compact Hausdorff space and the algebra, remember, of complex functions, continuous complex functions. This is the functor in the opposite direction. You are making one of those dual. I usually think of the compact Hausdorff spaces as being the one that dualized. Well, constructively, what we were able to prove is the following: that there's a duality between commutative C-star algebras and homomorphisms between them, and the dual of the category of compact, completely regular locales and maps of locales. So this is what Martin was sort of hinting he'd like to call spaces. I would like to call them spaces too, and then I'd like to call the lattices locales. I never quite have the courage to do that, but I have a basic aversion to using the word frame. Perhaps Isabel taught me that, and so I shy away from the skeletons and the bones. So again, you go from a commutative C-star algebra to this locale we're going to identify, and to each compact, completely regular locale, the continuous complex functions on it, and these are what give you an adjoint equivalence of categories. Of course, there's a bit of work to do to explain the terms involved, but on the face of it, this looks very, very similar to the classic result. And of course, if you actually interpret this in sets, or indeed in any topos with choice, then you will just recover the classical thing, because compact, completely regular locales in the presence of choice are all just compact Hausdorff spaces, and the commutative C-star algebras we're going to define, those are all just ordinary commutative C-star algebras. So, what are the constructive nuts and bolts that we have to deal with? The first is we need to talk a little bit about norms and semi-norms. Not much problem with the involutive algebra bit. Anything algebraic goes very, very nicely in a constructive context. My rationals do come out as rationals, well, nearly, not quite over the face, but they're trying. And so the idea of a semi-norm is that you axiomatize the open ball about the origin of radius q for each rational q, each positive rational q. The other thing we're going to have to be a little bit careful about is that the involutive algebra, to start off with, is only going to be an algebra over the complex rationals. As soon as we bring in completeness, that's going to whip up to the ordinary complexes, but without that we have to reduce things a little. I'll say in a moment why we're looking at open balls, not normal norms as functions into the reals. But they're actually, the axioms are, once you use them, they're really very, very nice. Because they tell you what you actually want to know about the norm. The whole purpose of the norm is it gives you a topology. And so knowing open sets is very, very helpful. So everything lies in some open ball about the origin. In other words, everything has a norm, classically. If A lies in open ball of radius q, A dash lies in that of radius q dash, then when you add them, you get something that lies inside of that of radius q plus q dash. That's just the triangle inequality on norms. And so on for each of these things. 0 lies in every open ball. 1 lies in all open balls that have radius bigger than 1. Conjugation, I mean the involution, keeps you inside the open ball you're in. And they are open because of the thing bottom right, that if you lie in an open ball, then there is a rational slightly smaller than the radius you've chosen, such that you lie in that. So we're really re-axiomatizing norms, not as a function, but as the topological content. So a very reasonable thing to do from a constructive point of view. Completeness, I'm afraid, also needs a bit of work. In working out, again in Montreal, this was in the spring of 1973 when Mars Tierney was there and was giving some lectures, having put right what the real numbers should be, the question was, well, what are the other ways of constructing them? You know, well, they must, for instance, be Cauchy sequences on the rationals. Not a bit of it. Cauchy sequences are not enough, basically because in the usual toposes you're dealing with, you don't have countable choice. So although you know something exists that is close to the real number you're describing, within 1 over n of it, you can't actually pick a whole sequence of them getting closer and closer and closer. And as always, or as in many situations in mathematics, if you can't pick something, then you choose all the things that existence tells you you could have picked from had you got the technology to do the picking. So what this says is assign to every natural number the things that approximate the element that you're trying to describe, that are within 1 over n of it, in a Cauchy sequence sense. So that says that whatever stage in picking the sequence or not you are, there is something that you could have picked at the nth stage, and these satisfy the natural Cauchy property that however close you want all the possible choices to be, beyond a certain point, there's always a point in the sequence of sets of possible choices that allows you to do that. So you define these Cauchy approximations, surrogates, constructive surrogates for Cauchy sequences. You then talk about such a thing being convergent to an element. You can then talk about completeness if everything does converge to a unique element. And that uniqueness if you've got a semi-norm and you've got something that is complete, then actually you have that condition down there, very, very non-geometric one, that is satisfied, that says that you've got a norm of it. Okay, so in a certain sense, we're never going to impose norm, because we're going to look at complete semi-normed involutive algebras, and they're going to have the semi-norm being a norm because of the completeness. So a C-star algebra is a complete semi-normed involutive algebra that then satisfies the additional condition that you have to put on with norms. For norms, it will be that the norm of A is equal, its square is equal to the norm of A times A involute. Okay, so in terms of open balls, it's expressed in that form there. And we're going to be concerned, well, just before the end, with those that are commutative. We also need to know something about compactness and complete regularity for locales. I'll try and skip this through because either you know these things really or you're not going to get it back quickly. But remember, compactness is easy enough. You know, that every covering has a finite subcovering. The rather below relation is that thing I said. V is rather below U if its closure is contained in U, but we can write that down constructively. The W that satisfies this can always be taken to be the pseudo-complement of V. Completely below, as we always referred to it, V U, says that you've got an interpolation from, subscripts don't seem to work too well here, between V and U, and that should remind you of Urison's lemma. And that's indeed exactly what explicitly it's going to be used to do at the moment. We then have that the locale is regular if everything is the join of things that are rather below it, or completely regular if things are completely below it. Next sad fact that one has to get used to in the constructive world is that although classically a compact regular space is the same as a compact completely regular one, in general that's not true, because although given compactness you can interpolate one thing between a given V that is rather below U, you can't go on and then interpolate things between each of those and between those and so on without having countable dependent choice, which in general we don't have. Looking ahead, the kind of topos that was being constructed by Spitters and Hoynen in their recent paper, not recent now, and implicitly by Andreas and Chris Isham in their account, those toposes do actually satisfy countable dependent choice. So in that particular case, don't worry. But as we'll see, when you're actually proving the Gelfand duality theorem, you desperately need the complete regularity. Again, I mentioned just now that in the presence of the axiom, full axiom of choice, compact, completely regular locales are spatial. They're just compact Hausdorff spaces. Or the topologies are.
Is there any example of a topos in which actually you can show that they're not the same thing, the compact regular and compact completely regular?
Yeah. I mean, don't ask me now. Sort of mind elsewhere, but I mean, they're very easy to find.
Yeah, there's an example somewhere in stone sets.
Yeah. I mean, it's well known. Okay, so now let's get one of the functors we want. If you have a compact, complete regular locale, let C of M, mysterious because I know why that's a different fun. C of M denotes the set of all maps of locales from M into, that should be C as well, where there we mean the locale of complex numbers. The locale of complex numbers in the category of locales and maps of locales has internalized operations of addition, negation, zero, multiplication, identity, conjugation, and so those can be tacked on the right side here to make the algebra of continuous complex functions on M inherit those things. So it becomes a commutative, involutive algebra over the complex rationals. It can also be given a semi-norm. Very, very easy. The open ball of radius q in it consists of all complex functions, M to C, for which the inverse image of the open ball of radius q in the complexes, we can draw that, is the top element of the locale N. So all things whose inverse image is the top. And this assignment is nicely functorial and goes from the dual of the category of compact, completely regular locales to the category of commutative C-star algebras. One's having to do clearly any work there to show the completeness of that, but that's all relatively straightforward and that gets all the details from the papers. Well, classically there are two ways of forming the spectrum, which is the next thing that we've got to do to get the function in the other direction. And these are linked by the Gelfand-Mazur theorem. A theorem, incidentally, which you normally do prove by using some complex analysis to get the result that's given. We're going to come up with a very different way of getting it. And these two ways of getting the spectrum actually, by the Gelfand-Mazur, give the same result, and so we'll just call it the maximal spectrum. Well, the first of these, perhaps it's the one that has most interest for, at least as far as provocation is concerned, for this audience, is, well, it's really the one that I've almost done. Here this was a generic complex number, and I'm going to make it a particular element of a commutative C-star algebra. And we're going to look at the extent that multiplicative linear functionals that we're describing map that element, that given element, into a given complex rational open rectangle. So again, we're looking at that observable property. Of course, if we're really looking at observables, self-adjoint operators, then only the real part of this will have any effect at all. And if this doesn't overlap the real axis, as it were, self-adjoint axis, then you're not going to get anything coming out of this at all. But we are looking, the first thing you do is to say, well, if I'm looking at multiplicative linear functionals, what are the open sets that I naturally take? And they're the ones that give the weak topology. You look at all multiplicative linear functionals that map a given element into a given open. So in this case, we're taking the basis of rational open rectangles. That's what we take. And so we'll denote that subbasic open set of the topology just by saying, we'll make this an observable property. And we'll denote it by A belongs to RS. And we'll then formulate some axioms that those naturally satisfy. Now, the way you go about doing this is earlier I gave the axioms for a generic complex number. So the first thing you write down is a whole bunch of things that say this is a complex number. And then you add in things that say, oh, by the way, this assignment is additive, preserves negation, preserves zero, preserves multiplication, preserves conjugation, preserves unit, and has norm less than or equal to 1 because of that. So what you end up with is a theory that doesn't look particularly pleasant in this case. If you think of all of those as subbasic open sets, then I often say to people, ask your local functional analytic colleague, write down a complete set of generators in terms of subbasic open sets for the topology of the space of multiplicative linear functionals. They're not going to come up with it, but if you think of it in terms of a theory describing things, then indeed you can do it. But I think I'll just skip on from that. So, what you do as the first stage in that whole process is just, what I've done is taken the axioms for a complex number, and I've replaced the generic Z by
a particular element of the commutative C-star algebra, and I've done that for all the elements. So I have a proposition for each A and for each rational open rectangle RS, and for each A I write down the complete set of axioms that say that A goes to a complex number. Once you've done that, then you add on those other things, linearity, multiplicativity, norm conditions, and then you just eliminate the things that, the redundancies that are given there, and simplify the thing down as much as you get. And you may not think it looks particularly nice, but the thing I wrote down just now is workable. Now, the fact that you've assigned to each A something that gives you a complex number immediately says that we can get what we want out of this, a Gelfand representation. Each element of A, remember all of this is working inside of a tuple, so it's all going on internally, gives a complex function on, well, I might as well call it max A, although it's really n fun A at the moment, because max A is what it's going to be, the maximal spectrum in a moment. And before we do that, we can check out that indeed we've got a compact, completely regular locale by showing it's a closed, going back again to Martin's talk, closed sublocale of the locale of linear functionals of norm less than or equal to 1. Joanne Peltier and I proved an Allowed theorem for that. Again, just working with the theory, and it's quite interesting to go back and see how that works. So it is compact because it's closed, and it inherits its complete regularity basically because we're looking at things that go into the complex numbers, so that all works because of that. That last bit depends on something that Gelfand and I eventually call the continuity principle. Whenever you take an open subset, an arbitrary open of the locale of real complex numbers, I'm using subset where Martin used subspace, then you can write down a new proposition in your theory, some new notation. A belongs to you, in other words, it goes into you, the observable property that it goes into you when you look at the generic multiplicative linear functional. Just by taking the join, again, over all rational open rectangles that are rather below you, of the propositions that it goes into one of those. So it says that it goes into you if it goes into one of these, because this is the subbase for it. And that is notationally consistent, and it then allows you to check that indeed this gives you a complex function for every A, and you can then check out a certain amount of work that this is actually a homomorphism into the complex functions on max A. So that's the first idea. Think of the spectrum as multiplicative linear functions. The second is the maximal ideals, and that is equivalent classically to multiplicative linear functionals because of some very special features of commutative C-star algebras. The first thing is that the maximal ideals of a commutative C-star algebra are actually just the closed prime ideals. So the first thing we're going to think of is that the maximals, if you like to call them, are the open primes, where prime means the same thing as Mulvey was observing. The second thing is that every prime ideal, therefore, is contained in a unique maximal ideal, because the closure of a prime ideal is a prime ideal that is closed, hence is maximal. That's a very unusual thing, and whenever it happens in commutative ring theory, it tells you that the maximal ideal space is Hausdorff, even though you're using the Zariski topology. Prime ideal space almost never, prime spectrum, almost never Hausdorff, but if you have that property of containing a unique maximal ideal, then you do get that the maximal ideals are Hausdorff. Classically, every multiplicative linear functional gives you a maximal ideal, take its kernel, as I said just now. And the Gelfand-Mazur theorem says that if a commutative C-star algebra is a field, and the quotient of a commutative C-star algebra by a maximal closed prime ideal is going to be again a commutative C-star algebra. And if that's a field, then it's necessarily the complex numbers. And canonically, because we have the complex numbers already included in the scalars. And what this says classically, immediately, is that every maximal ideal of a commutative C-star algebra is the kernel of a unique multiple linear function. So therefore, and this also goes over to the topology, therefore these two things are the same. Now, how do you get closed primes? Rather briefly. Well, it's actually really something to do about the complex plane. Because, okay, this is one set of generators for the complex plane. Well, here I just have a little bit of the complex plane, okay, a bounded region. So I'll give you another subbasic collection of subbasic sets. Take a given complex rational, which I'll just happen to call lambda, and look at all things that are outside the closed ball of radius q. Now, so we're looking at this bit, at least within this bounded area. Now, there's a very obvious trick to play that says we need only ever, once we get to using this with complex numbers and asking does an A map into this gadget, let's call this A lambda q. So if we're, sorry, not there, if we're away from this by at least q, we are going somewhere out here. So suppose that A maps into that, and now start introducing propositions for each element of a C-star algebra that says that A belongs to lambda q, is at least q away from lambda. Then the first thing you can say is, by considering A minus lambda 1, and just say that that is away from 0 by at least q, then you need only ever consider propositions of this form. Okay? So what we're going to do is to have an awayness notion on the complex plane, into which we're then going to put elements of the C-star algebra. And we'll see that in any bounded region of the complex plane, these things actually generate the topology as well. Clearly, all the outside of this can be filled up by these, but the question is, how do you do it the other way around? Well, first of all, these are the axioms. We're actually axiomatizing what's called a conorm. And this conorm then turns out to be the same thing as a maximal ideal. Well, sorry, it's the theory of maximals. It actually goes back to something that Scott pointed out at a certain point, that the complex numbers inherit from the decidability of the complex rationals a high degree of link between equality and inequality. Again, going back to something Martin was saying. And the reason for this is that the complexes are both a field in the constructive sense that's used in that respect of anything that's non-invertible being 0, but also a local ring in the sense that if the sum of two things is invertible, then either one is invertible or the other is invertible. So that is why this awayness is coming in. And that can be expressed by the openness of it by an axiom, sorry, that maps us into the locale of multiplicative linear functionals by taking one of these things to, well, the propositions that flesh it out. And we can then come back to just propositions that involve an AQ, and we can show that those two things are essentially the same. Two theories are equivalent. And the proof is like this. I said that the outside of this could be covered by these, but if you want to, within a bounded area like this blackboard, you just put in 4 things like this, and you look at the conjunction of the things that lie outside these disks, so that is here, that barreled area, and then you just allow those to go out to infinity and take the join of all of them. And that basically says that provided you're in a bounded region, everything works fine. Now I have to move rather quickly. So we have these dual aspects, and we can now get two adjunctions. One of them is the Gelfand representation we've already got. The other is taking a compact, completely regular locale, going to the maximal spectrum of the complex algebra, and that just takes the proposition to the inverse image of RS under the complex function that is the element that you're taking. So that gives a map of locales from M to max Cm by defining a map between propositions in the other direction. And that latter thing is both injective and surjective. Injective by essentially using Urison on the complete regularity, and surjective by a straightforward denseness argument using compactness. And the first of those is isometric from basically the observation that you have a generic functional into the complex numbers of the topos, and you then have basically a Stone-Weierstrass theorem that says that if you have a subalgebra of a commutative C-star algebra, well, of the commutative C-star algebra of complex functions on a compact complete regular locale, you say it separates the things if it satisfies a condition written like that. You can prove by a delicate argument involving finite partitions of unity that for any closed involutive subalgebra of a commutative C-star algebra of complex functions, which separates the locale that's underlying it, then it's necessarily the whole thing. And you do that by working with, you think of complex functions on max A as being the global sections of the complex numbers, the object of complex numbers, in sheaves on that thing. So the thing then works very, very nicely because you get something that is A, closed, and B, it already contains something that is dense, namely all the rational value function, complex rational value functions. And that gives you that we have the Gelfand representation being an isometric star isomorphism. Just one last thought, or a few last thoughts. If we're thinking about this axiomatization of the maximal spectrum, then instead of writing A belongs to A0, what does that say? We're at least zero distance away from zero, at least a positive distance away from zero. So that says when we put an A in, that we're mapping into the punctured plane. Well, that really is exactly what the proposition A belongs to P in the case of formula prime is meant to suggest. And indeed, you can write down, given that A belongs to AQ is the same as A minus Q1 plus the positive part of that thing lying in the punctured plane, that is provable, it's equivalent to that. So that says we can only mention propositions of the form A belonging to P. The last one that we want to mention has to be written still in that form. But it can be written, you can show with a little bit of work, that you can replace that last axiom by the one I've written there. Whenever an element lies in the closure of the linear span of a number of elements, then A belongs to P is the same as the join of those. Sorry, I shouldn't be an implication going in both, entailment going in both directions there. And this basically says that we're describing open primes, hence the constructive equivalent of the closed prime ideals, which of course are the maximal ideals. Now I can't finish without making one little remark.
suppose we take that theory and we just make a little change. See if you can spot it. Did you get it that time? If I flash it hard enough, it'll come. Okay, replace the conjunction, the meat of constructive logic in the sense of locales, a commutative logic, with the and that we use in quantums, a non-commutative and conjunction. Then what you actually get out of this same theory, change nothing, just leave it exactly the same, is the quantile that is what's become known as the maximal spectrum of a non-commutative C-star algebra. It's the quantile of closed linear subspaces. This is a quantal space within terms worked out by Gelfand and myself. And the points of it, non-commutative points of course, are the equivalence classes of irreducible representations of the C-star algebra A. And there's a nice Gelfand representation there that represents it in a non-commutative algebra of continuous complex functions on max A. That non-commutativity is because the multiplication doesn't come from complexes, it comes from A, which actually is what's going on, if one did but know it, in the commutative case as well. It really comes from the other side. But that takes us away from the orthodoxies of today's meeting. Thank you very much.
Any questions or comments?
Can we have lunch?
Maybe violating the orthodoxies further, I would like to get a bit more about this multiplication, the non-commutative case. So it's always easy in the commutative case because, well, the quantiles, how do you get at the multiplication?
You get at the multiplication basically because it's built into the quantile. Because the multiplication of the quantile is got just from the multiplication of the C-star algebra. You're taking a closed linear subspace and you're taking another one and you're taking the closed linear subspace that consists of all products of the two things. It is this that gives rise to the multiplication. It is difficult to do that in the abstract sense. You know, in other words, we have two of these things, this is the way we do it. I mean, I still scratch my head over exactly how you pick out the right thing. Because you've got subspaces and you've got to deal with a correct product element. But that is the way that the multiplication works when you have a C-star algebra. So, for the statement that I made here, that given any C-star algebra, you have this Gelfand representation and you have this product, that's the way it comes from. So it's coming out of the existing thing via the quantile. Okay, but it's because you're working with, as it were, the inverse image map.
Yes.
And the inverse image map is actually going from the complexes into the spectrum. And the spectrum, unlike in the commutative case, has this multiplication in it. I mean, it's exactly what happens in the commutative case, in that if you regarded the spectrum in the commutative case as still being a quantile, that's the way the multiplication comes up easily. In that slide that says, here's multiplicative functionals, it all looks, well, reasonably okay until you get down to the condition that says, this is the thing that says it's multiplicative. And it's the same problem we always run into, that addition of real numbers is simple. Multiplication of real numbers, we have to go into cases, or we do the other thing, which is just to slip down to the rationals and then say, well, it exists by completeness. Maybe just take the completion of that thing. But and the reason why it's, you know, why it's difficult in that theory is because we're doing it in the
locale context. If we did it in the quantile context, it would be extremely easy to say what the product of two things is, without bringing in the multiplication. In other words, you don't need the multiplication of the complex numbers to get, even in ordinary Gelfand duality, the product of two Gelfand transforms. Okay? It comes from the, what you're really doing is taking the quantile that is the spectrum and then saying, hey, things are commutative today. It's all right, we can work with the locale. You reflect it down into locales, and that's where that would then look very, very messy. So what do we do in locales? We put it all back onto the right-hand side. Okay, it's that kind of thing as well.
I just wanted to make one small historical point. I don't think that the Mulvey-Tierney proof of independence of the continuum hypothesis was actually affected by the fact that Tierney originally got the
No.
Because the continuum hypothesis is not a statement about the continuum.
That's why I was very, very careful to say that what they did was fine.
Yeah.
But when they tried to give a talk about it, it went severely wrong.
But not.
Well, yes. Sorry, it went wrong in the sense that the talk was not right.
Yeah.
Statements made were incorrect. But in the case of the spectrum, it was.
Okay. Well, let's thank Chris again. And,